Simple linear regression, week 11. Regression analysis is a form of modeling technique used to investigate the relationship between the response variable and one or more predictor variables, while it can be used for prediction as well. When you have got two variables, the simplest one that you can always remember would be height and weight. So we want to know the relationship between height and weight for a set of people. And then height will be the predictor variable and weight would be the response variable. In addition to obtain insights regarding significant relationships between dependent variable and independent variable, regression analysis gives us information about strength of impact of multiple independent variables on a dependent variable. Let's go back to height and weight. You have a set of people. You record each person, the person's height, the person's weight. All right. Now we say that height is predictor variable, weight is response variable or dependent variable, because height of the people, if a person is taller, it means that the person would be heavier. But when a person is heavier, doesn't mean that the person is taller. That's why the height would be independent variable. Now, in data science, for example, if we wanted to estimate the cost of service a company provides, considering all the different costs for the company involved, to provide that service, we can use regression analysis. When we start our regression analysis, we first fit a linear regression model, because there are lots of other different regression models as well. But why we first fit linear regression? Because it's easier to use as compared with other regression models. It's simpler to interpret the role of the independent variables, and we can obtain more statistics to be able to assess our model. Here, weight is equal to height times some number plus or minus another number. This is the simplest way of regression analysis, which is simple linear regression, line of best fit. So we say that there is a straight line relationship between height and weight. And then here we call it a constant or intercept for the equation of the line. And here it is called the slope, which is the gradient of the straight line. And then here height is the independent variable and weight is the dependent variable. Now in simple linear regression, two variables are involved. X, the explanatory variable, and y, the response variable. Now we write it as y is equal to beta 0 plus beta 1 x plus epsilon. Epsilon is the error term, and we assume in simple linear regression that the errors are normally distributed with the mean of 0 and the constant variance of sigma square, here we say. Now beta 0 and beta 1 are called the regression coefficients, and in practice they are unknown and have to be estimated, because we have got in our set of data we have got the x's and the y's, but then we calculate beta 0 and beta 1. Another thing that you have to know, normally you will see that in the line of best fit we don't write the epsilon term. When we have got it as what we do, we say expectation of yi is equal to beta 0 plus beta 1 xi, and we know that expectation, we take expectation from both sides of this equation, but because the expectation of error term is equal to 0, that one will be 0. So we are left with expectation of y, what we expect yi, observed value I, would have for its response variable when we have got the x value. Least square line of best fit or linear regression is a statistical method. In this method, the dependent variable has continuous values whereas independent variables can have either continuous or categorical values. Types of variables, continuous random variables are like height, weight, okay? But categorical variable like 1, 0, like blue, black, they are not measurable, but they can be categorized. It can be used for the cases where we want to predict some continuous quantity. For example, predicting a student's final results based on the number of hours studying their subject, or predicting the traffic flow of the customers in a retail store. And then here in this slide, these are beta 0, beta 1 are regression coefficients. Y is a random variable. It can be named as response variable, dependent variable, observed variable. X, which is a fixed value in our equation of a straight line, and it's explanatory variable or predictor variable or independent variable. Now, why do we say it is fixed? Because we give an X value, then we find Y in our model. Okay, once we have calculated beta 0 and beta 1. And here we say the error term is normally distributed with the mean of 0 and variance of sigma square. This linear regression model can be just used to provide insight into relationship between X and Y as well, or used for prediction. Now, in order to make it more understandable, let's say that we have got 3 observed values here. So the first point has got an X of 1 and Y of 6, and it is the blue dot here. The next point is the X value is 4, Y is 3.5, and it is in here. And the next value is X is 7 and Y is 4.5. Okay? Now we want to do the line of best fit. So the line of best fit, the line provides a method to estimate beta 0 and beta 1 so that it minimizes the sum of the squared residuals. See, when you have got the line of best fit, you can see that this is the observed value that we have got here. But on the line of best fit, we have got the point, the red point here. All right? And then the red point for the fitted value for this blue dot is in here. Okay? So, as you can see, the x's are fixed. The x's are 1, 4, 7. So, but the y's will be random and the y's are different here. They are in the red dots, they have different y's, but the x's are all fixed. Now, this is a model of these 3 points. Okay? Now, you can see the residuals. This is a positive residual. Why? Because the blue dot is above the red dot here, above the line of best fit. But here, we have got a negative residual. And because the observed value blue dot is below the fitted value. Okay? So, that is how we say that the sum of these residuals will be minimized in the simple linear regression. It's nice to understand what you are doing in modeling. Now, here we say that R, the residual, is Y minus Y hat. So, Y hat here is 5.4, but Y here for this point is 6. All right? But for this point, Y hat is 4.5, but Y is 3.5. Yeah? So, if sum of the squared residual, which is sum of our I square, would be the sum of each observed value, the y, yi, minus y hat I. Y hat is what you are getting when you produce the line of best fit, that regression line. Okay? And that line of best fit is beta hat 1, the formula is this one, and beta hat 0, the formula is this one. So we said y is beta 0 plus beta 1x plus epsilon, but y hat, which is the expectation of y, is equal to beta hat 0 plus beta hat 1 times x. Okay, so this is for you to understand what is this simple linear regression. Okay, so these are again some more information for you, that we say that to minimize the sum of the squared error, we have the sum of our I squared, sum of yi minus y hat I squared, and y hat is equal to beta hat 0 plus beta hat 1x. And here, to minimize this one, we substitute y hat into this equation. All right, so we have this, the quadratic expression, and then we can find the beta hat 1 and beta hat 0, but we are not going through that one. We are just knowing that beta hat 1 is covariance of xy divided by variance of x, which is equal to the correlation coefficient of xy times standard deviation of y over standard deviation of x, and that would be the formula. And then beta hat 0 is this one. But for this subject, you have to be able to enter the data in R, get the output, and interpret the results. Now, remember that in regression analysis, we fit a line or a curve to data points so that the square differences between the distances of the data points from the line or curve be minimized. And note that when we refer to the linear regression, we talk about linearity in the parameters of the regression equation, not the linearity in the independent variables. So the parameters of beta 0 and beta 1, as long as beta 0 and beta 1 are linear in your formula, you have got linear regression. For example, beta 0 plus beta 1 x1 or beta 0 plus beta 1 x1 square is still a linear regression. But if I have beta 1 square times x1, then we don't have the linear regression in here. Parameters are the unknown regression coefficients that are estimated from the sample.